In this video, we'll be talking about sustainable sequestration solutions to deter rising levels of atmospheric CO₂. Why study carbon sequestration? Currently, rising atmospheric CO₂ levels drive climate change, which causes environmental and societal impacts. A recent study reported that 2024 net CO₂ emissions were expected to reach 41.6 billion metric tons, which is up from 40.6 billion tons last year. Long-term carbon storage solutions are essential for mitigating these effects, and our goal is to identify the most sustainable sequestration technology using a structured evaluation framework. The four technologies. Biochar sequestration is biomass conversion to carbon-rich material for soil use. CO₂ hydrate formation is the formation of stable CO₂ hydrates under oceanic conditions. Carbon mineralization is the incorporation of CO₂ underground or in reactors as stable carbonates. And electric arc furnace sequestration utilizes steel slag to store CO₂. First, biochar. Biochar sequesters CO₂, producing through pyrolysis of organic biomass. This comes with dual-purpose benefits, which sequesters carbon and enhances soil health. Long-term carbon stability is a huge component of this technology, as it can sequester CO₂ for decades and even centuries. Some drawbacks being high initial capital investment as well as operational costs, not to mention potential environmental damage with habitat fragmentation, deforestation, and loss of biodiversity, as well as long-term soil impact and needs. CO₂ hydrate formation. This sequesters CO₂ through the formation of ice-like crystalline structures, which encases the CO₂. This occurs at stabilized under medium pressures and low temperatures, and uses magnesium catalyst to accelerate nucleation growth and enhance process speed. Similar to biochar, this has long-term stable storage with minimal leakage risk. Some of the drawbacks are high water consumption, expensive initial cost, limited scalability due to underdeveloped subsea technology. Here's a diagram of CO₂ hydrate formation, where CO₂ bubbles up from the surface and forms a crystalline structure in a hydrate foam. Carbon mineralization can occur in three different pathways: in situ, ex situ, and superficial. In situ injects aqueous CO₂ underground, which has massive scalability and abundant subsurface rock formations, but lacks value-added products and can induce leakage. Ex situ has many value-added products, including concrete, aggregate. However, it's very energy intensive and requires high temperatures and pressures. Superficial is spreading of alkali feedstocks along coastlines to react with ambient CO₂ in the air, which has many environmental benefits, but it's difficult to quantify sequestration or timescales. Electric arc furnace sequestration utilizes steel slag and carbonates the slag to sequester CO₂. In this process, supercritical CO₂ is injected into a reactor with steel slag, where the calcium oxide and magnesium oxide react with the CO₂ to form calcium carbonate and magnesium carbonate, a similar process to carbon mineralization. Some drawbacks include it's very hazardous to workers and the environment. In the process, granulation causes particles to go airborne, which can cause respiratory issues to workers. Heavy metal exposure can cause kidney damage and cancer, as well as the high temperatures and pressures can lead to hearing loss, not to mention the risk of an alkaline runoff due to the high calcium oxide concentration within the slag. Using these four technologies, as well as 9 indicators, we are then able to compare and analyze which technology is the best. Our 9 indicators occur across environmental, economic, and social topics. The environmental indicators are water consumption, environmental damage, sequestration potential, and net CO₂ avoided, which is our critical indicator. The economic indicators include capital cost, side product revenue, and scalability. Finally, our societal indicators our industry outlook, which includes potential for job creation in each technology's respective industry, as well as workplace hazards. From these indicators, we are able to conclude the most sustainable technology is biochar. This can be attributed to its strong environmental performance, where biochar has minimal water usage and adds additional benefits for soil health. Likewise, its long-term storage ability makes it a very viable technology, as well as its exceptional net CO₂ avoided, which can sequester 425,000 metric tons. For its economic viability, it has significant side product revenue as a soil enhancer and makes $100 million to $150 million annually. Likewise, the societal benefits include support to agriculture productivity and creates diverse job opportunities across biomass collection, pyrolysis, and distribution industries. Thank you.